Hello everyone, it's Mrs. Hanson. In this recitation video, I am going to work some Chapter 7 quiz questions that I thought were most commonly missed or had misconceptions. So you'll need your own paper out to perform some quiz corrections with me today, and this will serve as your recitation bonus point when you submit those into the Dropbox. So when ready, go ahead and proceed. We'll begin with our first question. In this quiz question, we're being asked to recognize a substitution reaction. And knowing that Chapter 7 was all about substitution, SN1 and SN2 mechanisms, versus elimination, E1 and E2 mechanisms, one of the essential skills is being able to recognize a substitution. And in this particular question, in this chapter, what we look for is what we called an alkyl halide that serves as the substrate, and its substitution will also need a nucleophile. The nucleophile, of course, will exchange places, will substitute for the halogen in the alkyl halide. So look for an electron-rich nucleophile and look for an electron-poor region, usually that carbon, that's attached to the halogen. So for instance, in this particular structure, I noticed that there is a carbon attached to an iodide. That iodide is going to be called the leaving group. And again, depending upon the mechanism and how it is achieved, the leaving group's job is to leave. We have a nucleophile that is going to attack, if you will, based on mechanism, if it would be an SN2 bimolecular and SN1 unimolecular mechanism, but an atom or group of atoms that breaks away from the rest of the molecule. That's what's known as a leaving group, taking a pair of electrons with it, and then, of course, the nucleophile then attaches itself to that alpha carbon. So as we look at our choices, we need an alkyl halide and a leaving group. Notice that this particular carbon, I'll call it carbon 1 in a 3-carbon chain. Carbon 1 is a polar bond because the electron density is being pulled towards the iodine. And just to kind of remind ourselves, we know that fluoride followed by chloride, bromide, and of course the largest halogen of all iodide, this makes the best leaving group simply because it can distribute that negative charge over the greatest surface area and stabilize the negative ion. And of course, fluoride we know is the worst of all leaving group. So as we look at our examples, the criteria is being met with the first choice, isn't it? And as a matter of fact, if we were to kind of work this problem and challenge ourselves a little further, ask yourself, what would the nucleophile look like to form, we have this new product that looks like this. I know it's not very neat, but that's all right. What we're being asked is what would substitute in place of the iodine to create this ether linkage? And so if you think about that, notice here, this is still carbon 1, 2, 3 with the methyl group coming off of carbon 2. What we have exchanged or substituted on is this particular region of that product. And so with a CH3 linked to an oxygen, that would have the negative charge, and you'd have to have a counter ion, probably something like a sodium or a potassium. Na+ would work fine. And then, of course, don't forget, we had the leaving group leave, taking its pair of electrons with it. It's not shown, it's not the organic product, but just to remind ourselves the leaving group really did leave. So the nucleophile would be something like CH3O negative, Na+, and the substitution occurred when we saw the electron poor carbon, because of the electron density here, having the nucleophilic attack in a substitution reaction. So your first quiz question was simply recognizing the pattern of substitution. Here we know that it would not change a location of a double bond, so we can throw that out. Here we had a double bond and all of a sudden it turned into an ether linkage, nothing to do with substitution. And here an ene became a saturated ane, nothing to do with substitution. Well, with that particular question, another common mistake was just recognizing an elimination reaction, the second big topic of our chapter. Recognize an elimination. Well, again, remember that you're starting with an alkyl halide as your substrate. And in that alkyl halide, you're going to form a double bond. So we're looking for elimination from a beta hydrogen that's adjacent to the alkyl halide position. So right away, I can toss out choice 2 and choice 4 because they're going the wrong direction, aren't they? We start with the alkyl halide and we form the double bond, the ene product. With structure 1 or choice 1, we have an alkyl halide, but it's been substituted with an amide, NH2 group, and I see no double bond form. So that's not correct. The criteria that meets the elimination is the alkyl halide, 2-chloropropane, forming the double bond in that propene product. So a base, notice this nomenclature as well. Now, instead of a nucleophile, as we had deemed in substitution reactions, we now refer it to as a base reacting with the alkyl halide. That base would be something like OH negative. And in the position, what we look for, as we learned, are what we call beta position hydrogens. So the base abstracts the hydrogen in the beta position, that bond collapses, and we formed the double bond. And remember, the leaving group leaves, even though you don't see it, we know that it's there. We just always write the organic products only. So the chloride is the other product. The leaving group leaves as the beta hydrogen was abstracted. Okay, great. In our next most missed idea or conception question, we had a few on kinetics. So it says, which of the following is the rate equation for an SN2 reaction? And that's actually a big word clue in this problem, SN2. I want you to think about what that means. It means bimolecular substitution reaction, right? Nucleophilic substitution. Bimolecular means we're going to have two molecules collide as part of the mechanism. Bimolecular, two things collide, so that both reactants are involved in the initial step, the rate determining step of an SN2 reaction. And so if you remember your kinetics from Gen Chem, we always start by rate is equal to K, where K is known as the rate constant. Since this is bimolecular, we have the alkyl halide substrate to the first power, first order with respect to the alkyl halide, as well as the nucleophile sodium cyanide, which is also first power. And that's just simply because their coefficients are both 1s. We had a 1-to-1 mole ratio. Bimolecular means there are two molecules involved in the reaction mechanism. One collision between two molecules. Just to kind of clarify as well, just thinking about what that would look like in terms of the kinetics graph, you would see one collision where we would have a transition state at the top of the energy hill. That transition state, if you think about this carbon right here as being the electrophilic center of that molecule, the electron deficient carbon because of the polarity of that bond. That carbon would be in the same plane as the leaving group, Br negative, is in the same plane with the nucleophile, which would be the Cn negative. And in the other 3 bonds, you would have a carbon-carbon, and then of course 2 hydrogens. That is known as the transition state of an SN2 reaction. We also said there would be an equal distribution of charge between the nucleophile and the leaving group. So we made sure to put those partial negative signs over the leaving group bromide and the nucleophile, the cyanide molecule. So our first choice, which one is the rate equation for an SN2? I can toss out choice A because it only represents one of the reactants. I like choice B, but we'll keep looking. Let's see. Choice C, no, they're not second power. Choice D, only one of the reactants. And choice E makes no sense either, one reactant that's squared. So the one that actually matches an SN2 is a bimolecular collision between the nucleophile, between the substrate, 1-bromopropane, and the nucleophile, sodium cyanide. Great. Well, in our next example, let's talk about protic solvents. Here's a quiz question that's simply asked, which of the following is a protic solvent? Well, so just think with me for a moment. What does the term solvent mean? The solvent of your reaction. It's just simply the liquid medium in which a reaction occurs, right? Sometimes we have water, an aqueous solution for our reaction medium. Sometimes we'll use a different solvent, an organic solvent instead of water. So just the term solvent, what are you putting your reagents into so that they have a mechanism for motion, collision, and a reaction to occur? Then think about the second part of that question, the one that says protic. What does the term protic mean? Well, protic comes from the word proton, and therefore it means that it has a proton, which is a hydrogen ion on it, which the following is a protic solvent. Look for the one that has an ionizable hydrogen ion. So first of all, do we see some hydrogen in this first choice? We do, but it's attached to a carbon, isn't it? And that a carbon to hydrogen bond is a nonpolar bond, and therefore the hydrogen is not ionizable. We need a polar bond. Ionizable. We need it attached to an O. An N would be good. I would say an F, the 3 most electronegative elements, but we know that this is very rare. So look for something that has an ionizable proton. I see one right here, the OH. That's a very polar bond between the oxygen and hydrogen, and it can set up hydrogen bonding between molecules, which is also a key feature of a protic solvent. So just some other comments about solvents. You can think about a solvent as being non-participatory in a reaction, and what that simply means, let me get that word written for us, non-participatory. It doesn't partake in the reaction itself. It's used to dissolve the reagents, but it's not a reagent itself. You can also have what is referred to as a participatory reaction. I'm going to really try to spell these correct. I did not spell that correct. Non-participatory, or, which is again just dissolving the medium and not partaking in the reaction, or participatory solvent, which means it is actually involved in the reaction. It could be the source of an acid, like giving a proton is another word for that. It could be a source of a base. Again, playing a role in the reaction itself. Source of a base would be to remove a proton from a particular reagent. It could be a source of a nucleophile. So these are the roles that solvents could play if they're playing a participatory role in an equation. So for example, if I add water and it is providing a source of a proton. Water is an example of a protic solvent that would be participatory, involved in the reaction by donating a hydrogen ion. Another example could be a hydroxide in water. A hydroxide ion could be an example of a participatory base which functioning to remove a proton from a substrate. So just kind of thinking about the role of solvents. What are we using it for? Is it just an example of a way for two mediums to dissolve so that they can have a reaction, or is it going to play a role in the reaction itself? If you see the term protic, look for an ionizable proton in that formula. Structure 2 is the only one that contains a proton, a ionizable hydrogen ion, by being attached to the oxygen. I see no other structure that has a proton and a polar bond that is ionizable. All right, great work. Let's look at a next example. Which of the following compounds will undergo a rearrangement in an SN1 reaction? So again, SN1 means unimolecular nucleophilic substitution. A unimolecular means we have one molecule involved in the rate determining step. And that rate determining step is always the leaving group must leave. And when it does so, it forms an intermediate called a carbocation. So again, just very distinct mechanisms. SN2 is a bimolecular collision. You have a transition state. Unimolecular is multiple steps. The first step is the leaving group leaves and forms an intermediate, and then we'll have the next step occur of either substitution if for an SN1 or an elimination if it's E1. So again, these are known as our alkyl halides, our substrates. Here we have a carbon attached to a chlorine. Here is the carbon attached to a chlorine or a bromine. These are the ones that we are looking at in terms of forming carbocations that would have an advantage of being rearranged. So I remember learning that a tertiary carbocation is the most stable, followed by the secondary, followed by the primary, which is the least stable. And so if a carbocation has an opportunity to rearrange either through a hydride shift or a methyl shift, it will. So all we're being asked really to look at is if the leaving group leaves, let's take a look at the carbocation and would it have an advantage of rearranging? So let's just kind of talk through these slowly. Here's number 1. At carbon number 3, of a 6-carbon chain, we have a chlorine. So 1, 2, 3, 4, 5, 6. When the leaving group leaves, we form a carbocation at carbon number 3. This is known as a secondary carbocation. Would it have an advantage of a hydride shift? And I can see there's no available methyl group on the beta positions. There's no methyl group hanging off, so I can't have a methyl shift, but I do have hydrogen, so I just want to, clarify hydride shift is the only thing on the table. And so let's just see what would happen. If carbon number 2 has a hydride shift, we would move from carbon 3 to carbon 2 for the carbocation. No advantage. It's still a secondary carbocation. What if we did a carbon number 4 hydride shift? And now at carbon 4, we have the positive carbocation. And again, it still remains a secondary. So there's no advantage to shifting because I haven't changed the number of substituent branches hanging off of the carbon that's positively charged. So structure 1, back here, structure 1 had no advantage of a shift. So no, I would not say that that would undergo a shift. Let's try looking at structure 2. And let me just take a peek. We have 1, 2, 3, 4, 5, 6. But at carbon number 4, there's a methyl. So let's just take a look at that structure. 1, 2, 3, 4, 5, 6. But here is a methyl. And this is where the leaving group would leave. It starts as a secondary carbocation. In beta position, we have hydrogens here, and we have a methyl group here, don't we? Well, if this undergoes a hydride shift, 1, 2, 3, 4, 5, 6, carbocation, if the hydride shift occurred between carbon 3 and 4, the positive sign now would be on carbon 4, and carbon 3 would now have the 2 hydrogens. So now all of a sudden I'm seeing something interesting. With that hydride shift, the original carbocation that started as a secondary, we could convert into a tertiary carbocation through moving the hydrogen from carbon 4 back to carbon 3. And as you look at all of the other possibilities, you want to look really just as a trick, look at the neighboring beta positions, if you will, and see if there's any advantage of swapping or exchanging out the positive sign with a nearby neighbor. In carbon, or in structure 3 here, we have a bromine, but next door we only have hydrogens. I'm not allowed to go 2 positions over, right? I'm only allowed to go 1 position over. And so the best thing I could do here was change the positive, and still it would remain secondary. So that's a no. Number 2, we said yes, definitely. Number 4, again, just 1 position over. I can't go down the chain, 1 position only. So again, even if I move the positive sign either direction, 1 step left or 1 step right, the carbocation remains secondary. And that is true here as well. But what's interesting here with this guy, of course it wouldn't undergo, because it is already a tertiary carbocation and thus is stable as is. So the only one that we determined would have an advantage would be structure 2, and it would do so because it can convert itself from a secondary to a tertiary carbocation. Great. All right, keeping up. Let's try a next one. Number 6 reads, what substitution reaction mechanism is most likely for the following conversion? I see 1, 2, 3, 4, 5, 6 carbon chain. On carbon number 2 is a methyl group and a halogen, a leaving group. On carbon number 2, on the product side, I see that the chlorine has been substituted into a hydroxide. So, all right, we know it's substitution. We can see here that the carbon attached to the leaving group is attached to 3 other carbons, isn't it? So this is what we called a tertiary substrate. The carbon that's attached to the leaving group is attached to 3 other carbons. So it's a tertiary substrate. What mechanism favors a substitution with a tertiary substrate? Now, remember, I have stressed in my video presentations the importance of really working to understand how to read this chart and have it just ingrained in your memory, right? To the point where you should be able to just close your eyes and see this chart. We can see that we have a tertiary substrate, and we know what it's going to do. It's substitution. And the reason that I can see that it's substitution is because the tertiary substrate forms a carbocation intermediate. So if I think about 1, 2, 3, 4, 5, 6, whoops, that's very messy, very quick and very messy. 1, 2, 3, 4, 5, 6. When the chlorine leaves, it forms this carbocation as a tertiary carbocation, very stable. So when the leaving group leaves, that's a unimolecular SN1 mechanism. We also discussed that for bimolecular collisions, that you want the least amount of crowding on that alkyl halide. To have two molecules collide, they need room to do so. And this target right here is very crowded because it's attached to so many other things. You can see that a primary substrate favors an SN2 reaction, and that tertiary substrate favors the SN1 reaction. So your choices here were SN1, SN2, both, or none. And in this particular example, the reaction favors the SN1 mechanism because when the leaving group leaves, it formed a tertiary carbocation, which is stable configuration for then the nucleophile to attach to that carbon. Again, 2 steps. Step 1, the leaving group leaves. Step 2, the nucleophile comes in to attach. And this is where you would have an inversion if it were a chiral molecule. This is achiral because the two groups here, this methyl and this methyl, are the same. But if we did have a chiral center, we would have an inversion of configuration if that were the SN2 mechanism. Of course, now we know that this, in an SN1 mechanism, as we were modeling here, SN1 mechanism, this is sp2 planar. So you have a mixture of products, don't you? We have a top and a bottom attack in a chiral center. Okay, great. Well, here's the next question. This one asks, which of the following is the strongest nucleophile in a polar protic solvent? Is it fluoride, chloride, hydroxide, and then you have sulfur hydride, all of these? So let's just kind of break it apart. Strongest nucleophile in a polar protic solvent. So again, think about what a nucleophile does. A nucleophile seeks an electron deficient species, right? It's going to seek the one that can easily accept the proton from that polar protic solvent. Let me write that with you. Whoops. How about this? The nucleophile will seek the one that most easily accepts the proton. So what does that mean? Think about what would fluoride look like if it accepted the proton. It becomes HF, HCl, HOH. And we could just write this H2S or all of these. Which one of those would be the strongest acid? The strongest acid would be the one that most easily accepts the proton and distributes the charge. So think about the trend, if you will, of kind of stabilizing the charge. we know that as you go down a group, fluorine, chlorine, bromine, iodide, and even next door to it, you have oxygen, sulfur. When you think about polarizability, think about the biggest atom being able to distribute the charge the best. So which one of these would be the biggest atom that would stabilize the charge? So we know that iodide would be the largest, and I would pick that as my example, but HI isn't a choice on the test. Next would be HBr. I would pick that, but it's not a choice on the test. So that leads me up to this particular group, H2S or HCl. Which one is bigger? Well, the sulfur is actually the bigger atom. Remember, atoms get smaller as you go from left to right. Since the sulfur is the largest in the group that's provided from the choices, this would be the strongest nucleophile in a polar protic solvent. Followed by HCl, followed by HOH, and of course the last place would be HF, the smallest of all. All right, so I hope that was helpful. I want to say that I missed a question. Oh, I did. I'm going to back up and say this is what was supposed to be question 7, but I flipped the screen too fast. Doesn't matter which way you order them, but it goes along with what was in this first question when I rambled about SN1 versus SN2 mechanism. We had a tertiary alkyl halide, so we said it would go with SN1 mechanism. What substitution reaction for this particular compound would you then predict? And I picked this one because it really does make you think about what I see at a chart and always following. This would be considered a primary alkyl halide because the carbon that's attached to the bromine is attached to just one other carbon that then goes on to attach to more. So it's called a primary alkyl halide. And if I go up to this chart, primary alkyl halides undergo E2 mechanisms, bimolecular collisions. However, what's unique about this position is that it's resonance stabilized. Because it's resonance stabilized, you have an opportunity to form a very stable carbocation intermediate. So for example, when the leaving group leaves, you would have this carbocation position, right? The leaving group leaves, takes its electrons, and you have a carbocation. But it can be in dynamic, it's not equilibrium. It can be in resonance with, sorry I misspoke, a number of other structures that would allow us to move. So for example, the pi bond moves here, this pi bond moves there, and then we see that the positive charge can actually go into the next ring. So we could have it here. And then of course the double bond moves here. And we've then shifted the position of those double bonds. That's a resonance stabilized carbocation. As a matter of fact, you can keep moving that position down throughout the chain. So the resonance structure, you know, every time I move the next, whoops, again, I can go this way and just kind of keep going around the ring and put the positive sign then at the next carbon. And then on and on. It doesn't matter. We get the idea that the resonance stabilized makes that carbocation, even though it came from a primary substrate, it's a very stabilized carbocation. So in this particular example, because of the resonance, I would say it could undergo SN1 reaction because it forms a resonance stabilized carbocation. But it can also undergo an SN2 mechanism because it is a primary alkyl halide, and the nucleophile can successfully collide with the electrophilic center of the substrate. So this is one that I would say both mechanisms are possible. So I'm glad I went back, because that helped kind of one of these questions that says, you know, don't always say these charts are cement, because sometimes you just have to think bigger. And if you see resonance stabilized carbocations, that's a very legitimate carbocation configuration for an SN1 mechanism. Whew, okay, pause anytime, right? Just pause the video. Keep coming back when you're ready for more. I'm going to continue to work quiz questions to help you prepare for our exam number 2. No, it would be exam 3, chapters 7, 8, and 9. All right, let's look at this question. Predict the product for the following reaction. What do you see? Well, right away, I'm noticing this particular structure on our substrate. This particular substrate has a sulfur group in it, doesn't it? This substrate, and you can see with the sulfur double bonded to oxygen in both directions, attached to the oxygen leading up to a fluorocarbon. This leaving group is known as an alkyl triflate, and then the RUTF. And just to kind of let you know, this was discussed in our lecture in section 7.10. What typically happens is we see that we would have an OH group as a leaving group, and we said that's a terrible leaving group. So you'll tosylate it to make it a better leaving group. Or you could protonate the alcohol to make it a better leaving group. So when you think about the leaving groups, you see a sulfur. This is tosylate is what that's referred to. Tosylate means convert the alcohol into a sulfur group, which then is an extraordinarily good leaving group because it can stabilize the negative charge, the pair of electrons it takes with. And so you'll see a variety of these. CH3, you could have, like this one had CF3 in that particular section, or you could actually see a benzene ring and then another methyl group. So whatever is coming off in this position determines what type of tosylate compound that is. But the trick there is that what you really done is the step prior to this was to take this molecule, this alkyl substrate, and instead of having it with an alcohol group there, you substituted this off with a better leaving group, and that mechanism was discussed. And so now we can see that the nucleophile is Cn negative. Cyanide, again, the sodium is a counter ion, and it's in a solvent DMSO. And DMSO, a dimethyl sulfoxide, if you wanted to remember what it stands for, dimethyl sulfoxide, you can see that kind of in that particular section in this particular area. Just kind of realize that that is an aprotic solvent. I'll show it to you. This is DMSO, dimethyl sulfoxide, as the solvent. So just kind of think of that as an aprotic solvent. So what is it going to make? Well, the leaving group leaves, right? That's the function of a leaving group. So when the leaving group leaves, it takes its electrons with, and the nucleophile is going to substitute on. And the nucleophile that substitutes on is the cyanide. That cyanide, of course, Cn negative with the counter ion sodium, you just toss out the sodium, it's there to just balance charge, that's going to replace the leaving group. And you have to ask yourself, Is it going to have inversion or retention? Since you can see that we have a strong nucleophile and a weak base, that's what the cyanide is. So if you think about where that would fall, a weak base, strong nucleophile, cyanide falls into that category. And you can look at that then and say, well, that's going to be either an SN2 mechanism because we had a secondary substrate. Secondary substrate, weak base, strong nucleophile, SN2 mechanism. Therefore, we have to have inversion. So this original molecule was the dash. The nucleophile substitutes on in the wedge position. So expect an SN2 mechanism. Again, CN negative is a strong nucleophile, weak base. So that's favoring SN2. Recognize substitution with inversion, and therefore structure 3 is our choice. The only other structure that would have made sense is structure 1 if we wanted retention. And even if we had said SN1 occurred, you would have a mixture because you'd have a carbocation intermediate and you'd have a top or a bottom attack. And since 1 and 3 weren't an option, right? Number 2 doesn't make sense because the leaving group didn't leave. You put the leaving group way up here. That makes no sense. And over here, the leaving group didn't leave. You put your cyanide there. That makes no sense. The leaving group has to leave, right? This whole thing has to leave. It's called the leaving group. And what we'll substitute on is the cyanide. That is called the nucleophile. And we said it would have inversion because the mechanism favors SN2. Okay, you're doing great work. Stay with me. Take a break if needed. I'm working example quiz questions. Perhaps these are new to you. Perhaps these appeared on your quiz. And I'm just spending time with you to make sure that if you had questions on any of these, you can see them worked out. Number 10 deals with retrosynthesis. Retrosynthesis, right? Planning a product, thinking backwards. Provide the reagents necessary to carry out the following conversion. Well, what do we see? Everything in this structure is exactly the same except the last atom in the reactant. We have a chloride, so that's called our alkyl halide. And we see that it's been substituted with the azide ion. So this is substitution. I know it's substitution because the chloride has been replaced with the azide. Really what we're asking ourselves then is what type of nucleophile, N3 negative, would work in what type of solvent? All right, so right away I can see that choice A and B are the acids of the azide ion, right? They would be proton sources in this reaction. We want the nucleophile to be negatively charged, right? So that they are seeking a positive electrophilic center. So in the salts, NaN3, think about sodium as the counter ion. This is the anion. We want it to be negatively charged. So I can toss out HN3 in both water and acetonitrile because I don't want it to be protonated. I want the salt, so I have a source of the negative ion. So now I've narrowed the choice down to choice C and D. Do I want sodium azide in water, or do I want sodium azide in a nonpolar aprotic solvent. And again, if I can't see that, acetonitrile, that list of solvents I just clip art from your text, acetonitrile is a aprotic solvent. So let me stress this again. We don't want this molecule to form because it's no longer negatively charged. This stays in the molecular form, the protonated form, because it's a weak acid. It doesn't ionize its proton very well. That's what weak acids mean. It stays molecular instead of ionizes. So we want to avoid any source of proton, which would mean we have to pick a solvent that doesn't provide a proton to keep the nucleophile as N3 negative. When N3 negative attacks that electrophilic center, the leaving group leaves, and we've created a substitution reaction where the azide ion has substituted on to the position that the chlorine originally had. So we eliminated any type of source where the N3 negative ion would be protonated and therefore would not allow the reaction to occur. Look for an aprotic solvent to keep the nucleophile unprotonated. I'll do another. Here's a quiz question that asks us to predict the product for the following reaction. I have 1, 2, 3, 4, 5, 6 carbons in a chain, and at carbon number 3, we have a tosylated alcohol, TS. That tosylated alcohol, those were all of those sulfurs that I had talked about here, OTS, that's what this means. The oxygen has this leaving group on it that makes it very stable. We have NaI and acetone in step 1, and in step 2 we have sodium cyanide and DMF. Again, that is the solvent, the aprotic solvent. So what happens? Think time. Well, let's just take this one step at a time. Let's redraw what we have. We have this OTS up here, and I'm just going to draw down so I have room. And in the first structure, I have iodide ion. And again, sodium is the counter ion. Acetone is the solvent. Acetone is an aprotic solvent, just so that it keeps HI from forming. We don't want a proton involved. We want to keep that as a, as a negatively charged. So we have a secondary substrate. And then we have this weak base with I negative. So with this weak base, think the SN2 mechanism. So we're going to have inversion. So this was a dash, now it's an a wedge. So that's the result of the first step, sodium iodine and acetone. I negative serves as the weak base, and you can think of that as the strong nucleophile because this is substitution reaction. The I is going to have a bimolecular collision with that electrophilic center, and an inversion would occur. Step 2. Here we have Cn negative in its solvent, DMF, an aprotic solvent. This is also a strong nucleophile, weak base. So in this position, we also know that it's going to be an SN2 mechanism, strong nucleophile, weak base, secondary substrate. You must know that that is an SN2 mechanism. So we'll have inversion occur. And we're now back to the original dash that it started with. So you had inversion in step 1, and a second inversion in step 2. So the final product would have the cyanide end up on the dash. Again, eliminating choices. We said this was the result after step 1. This is the result after step 2. All of the other choices make no sense. I'll work another. Which of the following is the energy diagram for the following reaction? So an energy diagram, really what you're being asked is how many steps would you predict in this particular reaction? Is it going to be unimolecular, bimolecular? What's happening to get the OH into a cyclohexene? So when you just kind of pause and think about what's occurring. I know first of all that it's got to be an elimination because I see that a leaving group is left and we've formed a double bond. So it's an elimination. And when a leaving group leaves, it has to be able to stabilize the negative charge because it's going to take the pair of electrons with it, right? And we would have the beta hydrogen, one of those extracts and the bond collapses and there's the double bond. But we said that OH, the hydroxide, is a terrible leaving group. And in order to get it to leave, you have to tosylate it or protonate it. You have to do something to it to create a more stable leaving group. So in our first mechanism, we have cyclohexane-ol, the alcohol coming off of the carbon, cyclohexane, and to name it as an alcohol, it ends in OL, so cyclohexane-ol. And what we'll end up doing first is to protonate it. So let's use a strong acid. The strong acid is going to go and protonate the alcohol to make a better leaving group. Now you could also tosylate it. It doesn't matter. You just need to do something to it to make it a better leaving group. But that's step 1. The leaving group as an OH will not leave. That's rate determining step is too large of a step for it to actually occur. Now I can see that the leaving group would leave. And when it does so, when the leaving group leaves, it creates a carbocation intermediate. You could just say minus the leaving group. The leaving group leaves, step 2. And in this next step, I'll just go this way so I have room. The beta hydrogen is going to be abstracted by the nucleophile, whatever the nucleophile might be. Could be the HSO4. The HSO4 started as the acid, and we donated its proton to protonate the alcohol. It could then reach out and take out that beta hydrogen to just reprotonate. And when it did so, it formed the double bond. And there we have our product, cyclohexene. So this would be, abstraction of the beta proton forming the alkene. So how many steps was that? It was step 1, it was step 2, and here's step 3. So all of those energy diagrams make sense in terms of the mechanism being in 3 steps. But ask yourself, which one of those is the rate determining step? All right. And I said, the hydroxide will never leave because it's such a poor leaving group. But keep in mind, you eliminate that factor by creating a protonated form. So the rate determining step of any of these E1, SN1 mechanisms is when the leaving group leaves. And the trick here was to realize the leaving group leaves in step number 2, not step 1. So you're looking for the rate determining step. Which step had the leaving group leave that takes the highest amount of energy to break that bond and form the leaving group? Step 2 was when the leaving group left, and therefore reaction mechanism A represents the energy diagram for that particular pathway. The most common mistake was picking the highest energy was protonating the alcohol somehow, making it a better leaving group. I understand that because it is a poor leaving group, but still always look for the leaving group leaving having the highest amount of energy required. All right. I'll keep going for as long as you want to listen. These are all sample quiz questions for test preparation. Which of the following is the rate equation for an SN1 reaction? Oh, we've worked some of these. So unimolecular. Unimolecular means that the rate determining step is when the leaving group leaves. Right? So the leaving group has to leave. The leaving group is on the substrate, isn't it? This would be called the nucleophile. This is called the substrate, and the substrate contains the leaving group. Therefore, unimolecular equals one molecule, rate is equal to K, times the concentration of the substrate, because the substrate contains the leaving group. And that name is 1-chloro-1-methylcyclohexane, not the chloride ion, not the nucleophile, not both because it's not bimolecular. It's unimolecular where the leaving group leaves as the rate determining step. Perfect. We've really done a good job emphasizing that. Here's a question from our quiz that asks us to predict the major product for the following SN1 reactions. So with this question, we need to figure out the major product of an SN1 reaction. Here's the substrate. This is the electrophilic center. So here are hydrogen, methyl. The leaving group leaves, so there is my carbocation. Notice this is a tertiary carbocation, a very stable intermediate. So, all right, there's the carbocation intermediate. The nucleophile is CH3OH. What kind of product is that going to make? Well, remember that the substitution is going to occur, and so the electrophilic center carbon is now going to form a bond. Let me try to draw this again. Oh, that's terrible. That's a little better. CH3, nothing changed there. Here's the CH3, and down in this position, we have the new, what the nucleophile has been substituted on, so we get OCH3. So which one looks like that? Here it is. OCH3 is the nucleophile. So I'm looking for exchanging the leaving group into OCH3. That makes no sense. It certainly wouldn't be a bromine. The leaving group has to leave. Nothing else changed. The only thing that changes is taking this leaving group and putting on the nucleophile in its position. So that one, pretty easy. Which of the following compounds would undergo a rearrangement during a solvolysis reaction? Now, solvolysis just means plus water, right? Which of the following would undergo rearrangement? So when I think of rearrangement, I'm looking at a carbocation intermediate, either a hydride shift or a methyl shift, so that I can exchange either a primary or secondary carbocation into a more stable configuration. So this question might seem intimidating, but it's really just asking you, based on structure, which one would have an advantage of rearranging the carbocation intermediate. So I have to draw them. Let's try this out. Here's the first one, heptane. 1, 2, 3, 4, 5, 6, 7. On carbon number 3, we have an iodine. And on carbon number 5, there's a methyl. So when the leaving group leaves, you still have a methyl here, but this is where your positive carbocation is. So remember, you're only allowed to look next door. You can't go 2 doors down. You have only an opportunity to exchange a hydrogen with its beta position. Is there an advantage of exchanging the hydrogen? So in other words, I still have a secondary carbocation if I took that hydrogen, and if I place the positive charge here, it's still a secondary carbocation, so no advantage. Letter B, this one says cis 1 iota 3 methyl cyclohexane. Okay, I'll try to draw a cyclohexane. Cis means both up or both down. So 1 iodo, so let's put iodine pointing up at carbon number 1. And at carbon number 3 is a methyl, it also has to point up. So when the leaving group leaves, it would form a carbocation right here, and we can see that this is the methyl in both positions, you know, position to the left, position to the right. If I take a hydrogen, it's still going to remain a secondary carbocation, so that one makes no sense. Let's draw heptane. 1, 2, 3, 4, 5, 6, 7. And at carbon number 3 is a methyl, and at carbon number 3 is an iodo. So actually that would not undergo a shift or rearrangement because it would already form a tertiary carbocation. So minus the leaving group, and he's all set. So that's not our choice. Let's keep going. 3 iodoheptane. 1, 2, 3, 4, 5, 6, 7. Here's 3 iodoheptane. Remove the leaving group, and you get a secondary carbocation, but nothing interesting next door, so no rearrangement there. Isn't it the way it always goes? It's probably the last choice. Let's check it out. Heptane. 1, 2, 3, 4, 5, 6, 7. Carbon 3 is an iodine. Carbon 2 is a methyl. There it is. Something interesting right next door. So when the leaving group leaves, I originally get a secondary carbocation, but it can undergo rearrangement through a hydride shift and make it into a tertiary carbocation. So this is the one that would undergo rearrangement by converting a secondary into a tertiary carbocation through that hydride shift. Whew, excellent. This concludes my test review from Chapter 7, working quiz questions out of the test bank from Chapter 7. I've worked 15 examples with thorough explanations. I hope you take the time to go through them and take good notes. Submit those notes into the Dropbox for your LA review sessions for your bonus point. Send any emails to me that you have if you have further questions. Thanks for playing. Bye.